Okay, one more problem on continuous beam. First I will read this problem. This problem was asked from November 2016 for 17 marks. Continuous beam ABCD simply supported at A and D. A and D are the end supports. Is continuous over B and C. Beam supports a superimposed load of 12 kN per meter, okay, and dead load of 15 kN per meter, and that load is including sulfate. Use M20 and Fe415, okay. Length AB is 5 meter, length BC is 6 meter, and CD is 7 meter. Now the lengths are different. Then how to solve the problem? The previous two problems are having 3 spans, but the spans are same. Now in this problem, the different values of spans are given. Then how to solve this problem? I will tell you. Draw the details of longitudinal section and cross section with reinforcement details. Okay. So let solve this problem. Solve this problem. Okay. First, I will draw the cross section. Sorry, line diagram of beam. First, I will draw the line diagram of beam. Okay. So line diagram is. So this is a 3-span beam. Okay. S. So this is support A, support B, support C, support D. The first span is of 5 meter. Second span is 6 meter. Third span is 7 meter. Okay. And it having the load. So the dead load is I will write that dead load is 15 kN per meter. Okay, and the live load is 12 kN per meter. 12 kN per meter. Now, how to solve this problem? All procedure is same. Whatever we have adopted in previous two problems, that same procedure to follow. But remember that the spans are different. That means you have to consider the different spans. Now, how many bending moments you have to find out? First, end span moment AB you have to find out. Okay, but again you have to find out the end span CD bending moment because the span is different. Okay. Then again find out the interior span BC moment. That means 3 bending moment related to span. Okay. Now next to end support B. Now next to end support B is related to these two spans. So while calculating the support moment at B, you have to consider the average of these two spans. And you have to find out the support moment at C, because these two spans are different. While calculating the bending moment at C, you have to take the average of these two spans. That means you have to find out the 5 bending moments, 3 span bending moment and 2 support bending moment. 5 bending moment you have to find out. Okay. Now the ultimate dead load is that is 15 into 1.5, this 22.5 kilonewton per meter. Okay, and ultimate live load is 12 into 1.5, it is 18 kilonewton per meter. Okay, in previous problem we have converted the bending moment ultimate. You can use that approach, or you can directly first convert the load into ultimate condition, and then you have to use these direct load values in bending moment coefficients. Okay. Now first you have to do the analysis. Okay, I will check. Okay, so these are the correct values. First to do the analysis. Okay, analysis of beam. Analysis of beam. In analysis of beam, you have to find out the 5 bending moments. 5 bending moments. So first is the end span bending moment. End span moment. End span moment AB. First moment is end span moment AB. So what is the formula? That now you get directly mu. Okay. End span moment AB is 1 by 12 W dead L square plus 1 by 10 W live L square. Okay. So this is the formula. We can take this value from table number 12. So 1 by 12. So converted dead load is 22.5. End span is 5 meter. Then 1 by 10. Converted live load is 18. Span is 5 meter. So already I have calculated this value to save the time. So end span moment AB, the bending moment is 91.87 kilonewton meter. Please check this value. Okay. Now next is end span. Next is end span. Next is end span moment CD. Next is end span moment CD, because CD is having different span value. Okay, so you have to use same formula. It is 1 by 12 W dead L square plus 1 by 10 W live L square. So 1 by 12. Dead load is 22.5. Now but to put the span 7 meter. 7 square plus 1 by 10 into 18 into 7 square. So already I have calculated the value. To save the time, it is 180.07 kilonewton meter. 180.07 kilonewton meter. Okay, is it? Now, interior span. Now, interior span BC. The moment for interior span BC, but the coefficients are different. The coefficients are 1 by 16 W dead L square plus 1 by 12 W live L square. Okay, refer these coefficients values in table number 12. Okay, now 1 by 60 dead load is 22.5, but span is 6 meter. Span is 6 meter plus 1 by 12 live load is 18. Span is 6 meter. So already I have calculated the value is 104.64. 104.62 kilonewton meter. Please note these values. Please note these values. Now you have to find out the support moment. Okay. Then support moments. Okay. Now moment on support. Moment on support B. Moment on support B. So what is the coefficient? It is 1 by 10 W dead L square plus 1 by 9 W live L square. We have these coefficients from table 12. So put the values. This 1 by 10. Dead load is 22.5. Now you have to find out now you have to put the average value here. So 5 and 6 nothing but it is 11. Okay, half of the 11 is 5.5. So 5.5 is the average value. So to put here 5.5 square plus 1 by 9. Live load is 18 and 5.5 square. So average span is 6. plus 5 divided by 2, it is nothing but 11 by 2, nothing but it is 5.5 meter. This average value you have to put here. Now I have the value, already I have calculated this value to save the time. Okay, next to end support B, it is 128.56 kilonewton meter, and next is moment on support C. Moment on support C. So the average value is 6 plus 7. 7 plus 6 divided by 2. Okay. 13 divided by 2. Nothing but 13 divided by 2. It is nothing but it is 6.5 meter. 6.5 meter is the average value. Okay. 7 plus 6 is 13 divided by 2. Average is 6.5. Now you have to use the same formula. It is 1 by 10 W del L square plus 1 by 9 W like L square. So 1 by 10 dead load is 22.5 into 6.5 square. Okay, it is 1 by 9. Live load is 18. It is 6.5 square. So now I want to write this value here. It is 179.56. 179.56. So this is the bending moment at next to end support C. Bending moment at next to end support C. So this is the analysis. This is the analysis you have to do before design. Is it clear? So now you have to put these all bending moments at particular location. 91.87 is the bending moment at end span. It is 180.07 is the bending moment at CD. 104.62 is the bending moment at BC. So here 128.56 the bending moment at B. Okay, and now I want to rough this. 179.56 is the bending moment at this support C. Bending moment at this support C. Okay. So now I will rough this. Now I will rough all these values. Now what to do? Now you have to find out the steel. Before that, you need the depth of the section. So 1, 2, 3, 4, 5. Collect the maximum bending moment, and for that maximum you have to provide the depth of the section. Now next step is design of beam. Okay. So first provide the depth for maximum bending moment. Provide that for maximum bending moment. So you know that mu max is equal to Ru max BD square. So the maximum value from these 5 values is 179.56. 179.56 into 10 raised to 6. 0.138 FC case 20. You have to assume the width of the section. Assume the width of the section 230 mm. Assume the width of the section 230 mm, and have to find out the depth. Okay. So this is the assumed value. So this is assumed value 230 mm. So while calculating all these things, we get the 532.6 mm is the effective depth. So round up this value is 550 mm, round up this value up to 550 mm, then assume effective cover 40 mm, assume effective cover 40 mm. Okay, so the overall depth is 550 plus 40, it is nothing but 590 mm. 590 mm is the overall depth. So what we get? So we get the width of the section is 230 mm, effective depth of the section is 550 mm, and overall depth is 590 mm from this calculation. Okay. Now what is the next? Next is you have to find out the steel. For this all bending moment, you have to find out the 5 steel. You have to find out the 5 steel for all bending moment. Okay. So steel calculation. Okay. Steel calculation. Okay. Steel calculation. So now I want to find out the steel. Okay. We have provided the depth of the section for maximum bending moment. So at these 5 locations, the beam is acting as an under-reinforced section. You have to use that under root formula to find out the steel. Simple procedure that whatever we have adopted in last two problems. Okay. So first is steel for end span AB. Steel for end span AB. The formula is AST is equal to 0.5 FCK divided by Fy 1 minus under root of 1 minus 4.6 mu. Okay. FCK BD square into BD. Okay. So 0.5 FCK is 20. Fy is 415. We know these values. 1 minus 4.6. You have to put the bending moment for end span AB is at 91.87. 91.87 into 10 raised to 6 divided by FCK is 20. Width is 230 and depth is 550 squares. So 230 into 550. So we have to find out the steel. Already I have calculated this value to save the time. That is 504.65 mm square is the steel at end span AB. So if you assume 20 mm bar, so 2 bars are required. If you assume the 20 mm bar, 2 bars are required. That means here 2 bars of 20 mm you have to provide. 2 bars of 20 mm you have to provide. Next you have to find out the steel for another end span CD. So steel for end span, now I have to only change the letters CD. Okay. All these ones are same, but the bending moment is different. The bending moment is 180.07. All other calculations are same. All other values are same. Okay. So only you have to change the value is 1108.99 mm square. After calculating this value, so if we assume the 20 mm bar, to get the number of bars are 4. That means you have to provide the 4 bars of 20 mm at this location. Like this, you have to do the calculation for 5 values. Okay, because you have the 5 bending moments. Now, steel for interior span. Next, steel for interior span BC. Steel for interior span BC. Same formula. Only you have to change the value. This value, bending moment value is 104.62 kilonewton meter. So the after doing calculation, the value is 582.83 mm square, and if we assume the same bar diameter, 20 mm diameter, 2 bars, 20 mm diameter, 2 bars. So here also the 20 mm diameter, 2 bars are to provide. Okay, so 2 bars here, 2 bars here, and now the 4 bars are here. Like this you have to provide the steel. Next is steel for support, steel on support. Again you have to do the same procedure. Steel for support B, steel for support B. On support B, only have to change the bending moment. It is 128.56. All other values are same, and steel for support B is 736.77 mm square. Okay, so now you have to assume if you assume the 20 mm bar diameter, so 3 numbers are required. So here 3 bars of 20 mm diameter at this location. 3 bars of 20 mm diameter at this location. Now steel for support C. Steel for support C. Same formula. Only have to change the bending moment. Bending moment is 179.07. 179.07. So the value is this 1104.95 mm square. 1104.95 mm square and 20 mm 4 bars. 20 mm 4 bars you have to 20 mm 4 bars you have to provide. So here 4 bars of 20 mm 4 bars of 20 mm you have to provide. So this is the design. This is a design related to flexure. It's a design related to flexure. This is design related to flexure. So while calculating the depth of the section, okay, that depth we have calculated for the graded bending moment. It is 180.07. Okay, is it okay? Now what to do? The next thing is the design of beam for the shear. Design of beam for the shear. Design of beam for the flexure is over. Now you have to design the beam for the shear. Okay. Design of beam shear. Design of beam for the shear. So first you have to find out the shear force. So the maximum shear force Pu is the maximum shear force coefficients are available on next to end support. Okay, shear force Vu on next to end support, next to end support. But we have the two next to end support. One is B and one is C, on which we have to consider the coefficient of next to end support. The coefficients are Vu is equal to 0.6 W dead into L plus 0.6 W live into L. So 0.6, we know the dead load is 22.5. Now you have to consider the greater span. If you consider the support B, the average span is 5.5, if you consider the support C, the average span is 6.5. So to take the greater average span is 6.5 plus 0.6, 18 is the live load. So the maximum shear force on next to end support C. So these are the calculations on next to end support C, because next to end support having the greater average span. Okay, so do calculation. Okay, so if you calculate this 0.6 into 22.5 into 6.5 plus 0.6 into 18 into 6.5 is 157.95 kilonewton. So this is the ultimate value. So this is the ultimate value. Okay, so this is the ultimate value. Now next is nominal shear stress. What is the nominal shear stress? Tau b. So we have the tau b is equal to Vu divided by B into D. Vu is 157.95 into 10 raised to 3 divided by weight is 230 and depth is 550. So by calculating this value 157.95 into 10 raised to 3, 157.95 times 3 divided by 230 into 550, it is 1.25 megapascal. Okay, 1.25 megapascal. Now tau c depends on PT. So what is the PT? PT is equal to 100 AS upon B into D. So what is the AS? So AS is the area of a tension steel available on where the maximum shear force is available. Our maximum shear force is available on next to end support C, and on next to end support C the tension steel is 4 bars of 20 mm diameter. So to take the 4 bars of 20 mm diameter area here, the width is 230 and depth is 550. So now what is the PT? I will calculate it. It is pi by 4 into 20 into 20 into 4 into 100 divided by 230 into 550. So it is 0.99. It is 0.99 means it is 1. For 1%, if you refer the page number 73, for 1%, the value of tau c for M20 grade concrete, it is 0.62 megapascal, and we have the value of tau c max from table 20, it is 2.8 megapascal, isn't it? Now you compare all these values. If you compare all these values, okay, now we want to it is 157.95 kilonewton. So here tau c max is more than tau b is more than tau c. 2.8 is more than 1.25 is more than 0.62. The shear reinforcement is required. Okay, shear reinforcement is required. Okay, so shear reinforcement is required. So directly assume 8 mm diameter, 2-legged stirrups, 8 mm diameter two-legged stirrups. Okay. So the spacing is that is the ASV. Sorry. VUS is equal to 0.87 Fy into ASV into D divided by SV. You use this formula. Now what is the VUS? VUS is the shear force for the shear reinforcement. Okay. So it is nothing but maximum shear force minus shear force taken by concrete. The maximum shear force is 157.95 into 10 raised to 3. Shear force taken by concrete is tau C BD. Okay, tau C is 0.62, width is 230, depth is 550. So what is the VUS? So VUS is, so I want to calculate it now. Okay, 157.95 into 10 raised to 3 minus 0.62 into 230 into 550. Okay, so the value is 79.52 kilonewton. Put this value here. 79.52 into 10 raised to 3. 187 Fy is 4 by 5. ASV is 1 stirrups bar diameter multiplied by legs. Already we know this value. It is 100.53. Depth is 550. Now to find out the SV. What is the SV? What is the spacing SV? I will calculate. It is 250. 250.79 mm. Okay. But the spacing should not be more than first criteria is 0.75 T. 0.75 T is 412.5 mm. Okay. Second is 300 mm. And last one is the minimum spacing. Third criteria is minimum spacing criteria. Okay, so we have that value, that is ASV divided by B into SV, 0.4 divided by 0.87 Fy. I think it is nearly 304 point something. They have calculated this value so many times. Okay, the SV is something 304 point something mm, 304 point something or 302 point something. It is more than 300. So if you compare these 1, 2, 3, 4 values, 1, 2, 3, 4 values, the minimum value is this. It is 250. It is 250. So you have to provide the 8 mm diameter two-legged stirrups, 8 mm diameter two-legged stirrups at 250 mm center to center. At 250 mm center to center. So this is the shear design. This is the shear reinforcement design. Now you have to sketch the reinforcement details. Last point. You have to sketch the reinforcement details. Reinforcement details. Okay. Now I am going to explain the cross section details of this problem. Okay. So for span AB, the bottom reinforcement is 2 bars of 20 mm diameter. You have to show like this. Okay. For span BC, the bottom reinforcement is 2 bars of 20 mm diameter. You have to show like this. And for span CD, the bottom reinforcement is 4 bars of 20 mm diameter. You have to show like this. That means 2 bars are running for span AB, 2 bars are for span BC, and 4 bars are for span CD. Like this, the bottom reinforcement is provided. Then on next one support B, the 3 bars of 20 mm diameter already we have designed. You have to show this bar, but these bars are provided for L by 4 and L by 4 distance only. At this location also 4 bars of 20 mm diameter to show at L by 4, L by 4 distance. Okay. But because of to anchor the stirrups, you have to extend the 2 bars from these 3 bars. At this end, 2 bars, extend the 2 bars in between this region and extend 2 bars at the end of this beam to anchor the stirrups. Minimum 2 bars are required at top to anchor the stirrups. Stirrups are 8 mm diameter, 2-legged at 250 mm center throughout the section. So this is the shear design. Now if you cut the beam at this location, section AA dash, 2 bars of 20 mm diameter to show. 2 bars of 20 mm diameter to show. Okay. At bottom 2 bars of 20 mm diameter you have to show. Width of the section is 230 mm. Overall depth is 590 mm. And stirrups are 8 mm diameter, 2-legged at 250 mm center. If you cut the beam at this location, interior span BC, mid span of BC, the section is same. That means 2 bars of 20 mm at top, 2 bars of 20 mm at bottom. So like this you have to write down section AA dash and section BB dash having the same picture. If you cut the beam just right of B, what you get? 3 bars of 20 mm diameter at top and 2 bars of 20 mm diameter at bottom. The section CC dash is like this: 230 mm wide, 590 mm depth, and 8 mm diameter 2-legged stirrups. Get it? Now if you want to cut the beam just right of this C, you get some different picture. That is 4 bars of 20 mm diameter at top and 4 bars of 20 mm diameter at bottom, and stirrups are 8 mm diameter, 2-legged, 250 mm center to center. Okay, the stirrups are same throughout the section. Width and depth is same, and considering the rectangular section. This picture is at cross section DD dash. And finally, if you cut the beam at mid of the CD, you get 2 bars of 20 mm diameter at top, 4 bars of 20 mm diameter at bottom, width is 230, depth is 590, and stirrups is 8 mm diameter, 2-legged stirrups at 250 mm center to center. Like this you have to show the reinforcement details and send it on site to erection.